Ready?
Want to start it?
Yeah, sure.
Hey guys, welcome to workshop 4 of our beginner workshop series. Today we're going to be covering logistic regression. And also, if you need the links for ACM AI, you can copy them. You can find them at this link here. We're going to leave it up for a few seconds.
Everyone go to the link. Oh. Everyone good? All right.
Okay, so first we're going to start to build an idea of the intuition behind logistic regression. So linear regression is generally used to predict continuous data. So house prices, maybe GPA, something like that, something that's linear. Logistic regression, though, is to classify categorical data, which is like this or that. Is this a cat or a dog? Is this a plane or a car? And so on. I don't. Oh yeah. Here's an example. Am I going to lecture tomorrow? Yes. So here's some of the data we might use. It's gloomy and rainy. It's 8 a.m. The class is at 8 a.m. I'm in a grumpy mood. I'm hungry. I'm telling my mom, yeah, I didn't get my midterm back yet, and I'd rather not stay in my sleep. And very few of my friends are going. Am I more likely than not to go to lecture today? Any thoughts?
Who says yes?
Who said? Okay.
Okay. Who says no?
Who said?
Okay.
We've got some water.
Interesting.
No, absolutely not. But the person who wrote the slides pays $60K, an international student. So yeah, the probability of me going is easily less than 50%.
Interesting.
Yeah. So, another example, what should I eat tonight? If you're a UCLA student who lives on a hill like I do, you know that there are several options. And even if you don't, like, there are many options as well. So here's some data. I'm hungry. I'm craving pizza. I am really impatient. I'm at Sproul, and I would rather not climb the death stairs. So here are some options. I assume you're familiar with most of these. These are just like the different like hill options for dining, and here are the chances. So I'm not the one that chose these, by the way, but you know, they're just like different chances. So as you can see, Denev is highest, probably because I'm at Sproul. I don't have to climb the death stairs, and so that's perfect. The Dre, on the other hand, I do have to climb the death stairs, so that's definitely gonna make it less likely. And so those are some of the factors that go into this. There was actually something I just go back.
Yeah.
So we call these options classes, and this is actually going to be really important as we get into what logistic regression is about. Next. Okay, so to summarize, logistic models handle categorical tasks like binary classification, or which is like our lecture example, do I go, do I not, or multiple category classification, like the dining hall example. Usually we use this for image classification purposes. So if you were to look at an image, you're basically asking the computer, is this like a bird or a lion, essentially, that kind of classification. And next one. So here are some actual examples of image classification. We use, one of them is the MNIST data set, which is a set of basically 28 by 28 digits. They're drawn to be like the digits that are possible. And Yeah, so that's how that works. And then another example, more practical example is email spam detection, which is to determine if an email is spam or if it's an actual legit email that you should read. And so this kind of classification crops up in all sorts of areas. So how does a computer actually do this? So first, we use an array of pixels, which is the image, as an input, and then we call each pixel a feature. And we'll get more into that in a minute. So the binary, so for image classification, if we have binary classification, we have two classes, and then the class label is 0 or 1. If 0 meaning it's one class, 1 meaning it's the other. So we're on the output. 1 is yes, 0 is no. And what we want to know is how sure are we that the predicted class is actually 1 or 0? And basically, we want the probability of the class being 1, and that's what we compute with logistic regression. So we use 0.5 as a dividing line. So if our probability is less than or equal to 0.5, we say that the object is class 0, so it's not class 1. And if it's greater than 0.5, it is class 1. So now the objective with with logistic regression is to actually find a model that predicts the probability that the object is in class 1 as best as we can. And as an aside, I guess I'll just ask, how do we get the probability of the object belonging to class 0 from this? Any thoughts? Yeah. So for those that don't know, a complement is basically 1 minus the probability. So if the probability is 0.4, 1 minus 0.4 is 0.6. That's basically how that would work. Are there any questions so far, by the way? Are we good? No? Okay. Next. So we need a hypothesis to find this probability. And for these kinds of classification problems, we can use something called the logistic regression model, and so that's and nothing else. But we use the logistic regression. And the next thing, one last thing is building off linear regression. Yes. So linear regression is that we want our hypothesis to be a function to output a probability between 0 and 1. Our current linear function maps, our current linear function maps to any real number, so negative infinity to infinity. It doesn't really work if we get like 100, for example, or -2, because it's not between 0 and 1. So how do we fix this? So what we use is something called an activation function. And here's an example of one. It's called the sigmoid function. You can see what the function actually is. It says, so the way it works is if x is negative, sigmoid x is less than 0.5. If it's greater, x is greater than 0.5. And also, as we can see, something kind of important here is the 0, x or y equals 0 and y equals 1. For any x, the sigmoid of x is in between 0 and 1. Next. Any questions? No? Okay, and now we're going to go to building the model, and for this part, we're going to have Nikhil take over.
Thanks, Wade. All right, so now that we have the basics of like what we're trying to do with the regression, let's go to actually building the model, right? So we have a linear regression, we have sigma, right? And so the question is, how do we combine these things together to create a model that we really want, right? And so again, x here, the input to our function. And so we don't want to just pass in our inputs, right? So like our inputs could be like, I don't know, for example, how hungry you are, how far you're from the net kind of thing, right? We can't just pass that in to this function, right? It doesn't do enough. We need our weights and our factors again, the actual learning. And so the question is, how are we going to actually add like our learning process, our weights and our biases to this equation? And so the idea is we're going to fit in our old process function, x times w plus b, into our sigma function. So basically we're turning our old output with negative infinity, and we're squeezing that down to 1 to 0 to 1, right? That's what we want, right? We want our output to be between 0 and 1, and if it's greater than 0.5, we'll predict class 1, otherwise we'll predict class 0. And so as you can see here, we have our old linear regression function formula, which is x times w plus b. Everyone familiar with that function from last week? 2 weeks ago, I guess. Yeah, and then also we're plugging that in into our sigma function to get a squeeze value from 0 and 1. Does that process make sense to everyone? This is pretty important to understand because this is like our model. That makes sense to everyone? All right, cool. And so, as I said before, if our prediction for output of sigmoid is less than 0.5, so below this mark, we're going to say it's a 0 class. Above this mark, it's a 1 class. So it makes it pretty easy for us to actually get a final output. We just plug it into sigmoid and see what the output is. That's good. And so, in a way, you can think of this model as basically like finding a conditional probability, right? It's a way of basically saying, what is the probability of the model being of class 1 given the input features? And so, we're basically kind of finding a distribution in a sense that we're trying to find a model that classifies this distribution well. And so, you can think of it as we're giving the model some inputs and it's trying to figure out how likely is it to be class 1 compared to this. So this is like a more probabilistic nature of this model that makes it more rigorous. And so with that in mind, we can think of our line before WT x plus b as like a decision boundary. And so in a sense, we want to learn a W and B such that this line essentially separates our two classes in place. Does anyone see any problems with this an idea? Like a problem with having a one line decision boundary? In theory. Yeah.
It only works for 2 categories.
That we can add, we can extend it in a way to make that. That's a kind of a problem. We can fix that a bit easier. I'm looking for something a bit different here. Yeah, exactly. So if our data isn't separable by like a straight line, it is not possible for us. We can't get a perfect model here. But for time being, we're going to assume that our data is linearly separable. And so our goal in this model in general is to find like a decision boundary that we can use to separate. And so it isn't exactly WTX plus B exactly, or that this line is, but we're using those weights, we're kind of finding a line that's similar to this. I won't go into the math of what this line actually is, but it's based on W. It's not exactly silk W. And so our next goal is to figure out how we can optimize this like decision boundary in a way. So the way we're going to do this is again gradient descent. And so last time we used MSE, y'all remember MSE last year? Yes, no, mean squared error. Sorry. Mean squared error thoughts. I'll run through it really quick again. It's basically we have our prediction y hat and our actual like wanted value y. We subtract them and we square that and we take the mean of all of those over all the samples. Basically, we're seeing how bad a model is compared to the target, and we're doing that for all the data points and squaring them all. And so that works for linear regression, but in our case with a sigmoid function, it's not as good. Anyone have looking at these diagrams? Anyone see any potential issues or see the issue with MSE in this case? Or just kind of hard to see. Any guesses, honestly, I probably can't do. That one. So. You mean for this graph or? Yeah, in a sense, kind of. It's not expanding on that kind of. Basically. It's on the next slide. I don't know. No, it's not. Come on. Yeah. So. Basically, the idea is that sigmoid, right? When it flattens out over here, like over here, our difference in like outputs is really small, right? And so when we apply MSE to this problem, we're gonna get really small, like actual changes in our output because when you go from like 4 to 6, the change in sigmoid is tiny, right? But when you go from like a normal output layer, the change can get a lot bigger, right? And so if you have to get stuck with like predictions that are like for like values that are closer to the side of the sigmoid, we're not gonna actually learn too much. We're not gonna improve our model much faster. So we're actually gonna introduce a new loss function. It's called cross entropy. It looks complicated. It says like a bunch of stuff, but we'll break it down in the next slide into simple parts. So same equation up there. Y has a prediction, so we'll predict. Y's are like true label value. And so it looks complicated. Well, let's imagine what happens when our target value, our Y value is 1, right? So when Y is 1, we get that 1 minus Y is 0, right? The second term cancels out, and we get -1 times log of Y, right? And so thinking about this logically, right? If our Y hat is actually, for Y hat is closer to 1, we're going to have an error closer to 0. And if it's not this further closer to 0, we're going to have an error. This log will be negative. It'll be a log of a small value, like log of 0.5, for example. And then we're going to have a negative sign. So if Y hat is less than 1, we're going to have log of a value less than 1. It's a negative value, right? E to the negative power is something less than 1, right? And so negative value times negative sign gives us a positive loss, so our function is doing a bit worse. But if we have a perfect prediction of 1, we get 0 loss. Does that part make sense, everyone? If we match our target of 1 to our label of 1, we get a perfect loss. Otherwise, we get a loss greater than 0. This is what we want, right? Same thing goes around here, where instead of the second term canceling out, the first term cancels out, and we get 1 minus 0 is 1 times log of 1 minus Y hat. And the same logic applies here, where that closer we are predicting 0, the lower our log. Does this concept make sense, everyone? We want to, if our Y hat matches our Y, we get 0 loss. But otherwise, we're going to have a loss that's a bit positive. This is what we want. We want to make our error better. If I want our mod nodes doing doing bad, it's not the difference. Is that concept clear? Thumbs up or not? Or thumbs down? All right. Cool. All right, and so we can do this over all of our data points. Let's say we have n data points, so we're going to sum our loss function. So this loss function over here is our function from last slide. We're going to sum that over all of our training examples m, and we're going to take the average of that. So 1 over m times sum of the loss. And so expanding that out, we get the bottom equation. That makes sense.
Yeah, it is.
All right, cool. So this poll was kind of, I think honestly a Zoom minute, but can anyone see what the correct equation is? It's kind of a, yeah. There a negative sign? I low-key think it's C, but right?
I think B is just the negative of C,
Yeah.
right?
So, I think C is correct answer.
C. Wanna check?
Sorry, guys. Tricky. I think it's C. Oh, we can check the side 2,000 ago.
Oh, wait, no.
This goes up before.
Okay,
Y'all are correct. Nice job.
it is B.
Harder than me. But yeah, it is a negative one. This is plugged in by just, but yeah.
Yeah.
Cool. Yeah, that makes a lot of sense, because we need negative a lot, so.
Yeah.
Good catch, thank you.
Yeah.
All right. So, sorry about that, but nice catch all of the guys. So now moving on to gradient descent again. So we have a loss function in the previous slide. We take the derivative with respect to W and B to figure out how to change our weights. And so I'm gonna spare you from the math, but that's what it should end up being. If you want to do the math, it does end up working out that way. Don't want to talk about it. We can talk about it after. So it's another day. But math does work out to these two equations, and so basically what we're going to do is that every concept we're going to update our weight by subtracting learning rate alpha times our derivative of with respect to W, and same for bias as well. Does that make sense, everyone? Gradient descent, familiar last week. Yeah. So for gradient descent, our goal is basically optimize our W and B, right? And so we have our W and B in our equation, which we're plugging into the sigma function, right? But at the start, they're really bad W and B, so we don't know anything about the data set yet, and so we don't know how to make our W and B yet. But what we're going to do is that we're going to update our W and B based on partial derivatives with respect to L with respect to W and B. And the idea is that the gradient, right, is the vector of all the partial derivatives, right? So the LBW and the LBB is all the partial things that are involved in L. And so the key math idea here is that if you follow the gradient direction, the negative gradient direction, you're optimizing the function the most, you're going down the cost function the fastest. And so that's the idea here, is that we're taking the gradient of L that with the W and the B, and then we're going to go down that gradient to optimize the list fastest. So going this direction that way is like mathematical reasoning is like the most steep slope going downwards on the function. So we're going to lower our cost function as fast as possible. And so we're going to follow that slope times the thing called learning rate that we can choose ourselves to figure out how fast we want to go down or how fast we want to update. And so if you do this over and over again over our training data, you can basically lower our cost function over time. Is that a better picture? Any questions about gradient descent? It's a pretty important concept. So if you have more questions, please ask, because it's good to talk about it. All good? All right. And so yeah, in our slide we will link to the full derivation. It's a bit complicated, but not too complicated. Just a bit of chain rule in there with matrices vectors. And yeah, we'll just go over it later if you all want to. Yeah. And so just putting it all together, the question is here, like what task is logistic regression best suited for our B-score? Predicting the house price, predicting whether to approve or deny a loan, generating pictures of dogs and cats, or facial recognition. Yeah, exactly. And why did you pick B? Yeah, exactly. We have two different ones. So yeah, A is linear regression for predicting natural number value. It can be anything from negative to infinity. B, as I said, is either a yes or no decision. So like, yes, we give the loan, or no, we don't give the loan. C is generation of things. So we're not going to do generation at all with linear regression. So we just cross that out. And B, probably closest to one, right, is facial recognition. So it is a classification problem, but a bit too advanced for this regression to handle, so we're not gonna include that. But it is still classification. But not for this, it's not good for everyone. Good job, everyone. Move on to the next slide. Yeah, so any questions about the model, gradient descent, or everything I covered in the last like 10 slides? Oh, for the, okay, can we go back this slide?
Which
Like
one?
the
This
loss function slide?
Oh, this one?
This one? These two cases? Yeah. So we have a function up there. So in y is one, that's like our target is one, right? So like we know the object is class one. And so we plug it into our loss function up there. And so as you can see, we plug it in. That first term, negative y is negative times 0, right? That first term is you cancel that out. Second term is 1 minus y, 1 minus 0 is 1 times log of that. So we can get rid of our second term, or sorry, get rid of our first term, keep our second term, and that comes down here. And so we have negative log of y. Oh, no. That way, that there. Oh, no. So this is this case, yeah. So we have 1 minus, we have this case right here. We get negative 1 minus 0 is 1 times log of 1 minus 1, right? So this is 1 minus 1 minus log, negative log of 1 minus 1. And so what's the best case here? The best case is if y hat is also 0, right? If our model says it's class 0 as well, the predicted value of 0, that's perfect, right? So in that case, our error is negative log of 1 minus 0, which is negative log of 1, which is 0, right? And so here our loss is 0. If, for example, our y hat is not 0, for example, y hat be between 0 and 1, right? So y hat is 0.5, for example, right? We get negative log of 0.5. And so 0.5 is negative 1, right? Or log of 0.5 is negative 1. If we're getting log 2, for now, it's just log 2 for now. So we get negative 1 times negative, they're a loss function of 1, which is what we want, right? So we want, like, if our model is off on its prediction, which is in this case, that we predicted 0.5 instead of 0, we want a positive loss, tell the model that's being bad. And the closer to loss our y hat is to 0, the less this error will be. And the same applies in the reverse with the y, y equals 1. Does that help with that? Or something else? Good question about that one. Yeah. It's also honestly kind of complicated, but once you like get into using it a bit more, it gets a lot more understandable.
Yeah. Any other questions?
In that case,
Anything?
see what time it is. We take a 5-minute break in that case. We'll come out with the game afterwards, but take 5 minutes or so. Yeah, get water, just chill.
Pause the recording. I can just pause it. So the people online, or the people that we watch later will hear.
How is that going? Okay. Here comes
I'm close now, close for the exam, but they're usually manageable, yeah. Yeah, like, it's like a 4-week midterm, so that's more, see that one. It's like a crazy, like, that must start. Yeah. Like most professors like allowing cheat sheets.
Yeah.
Yeah. It forces you to study. Yeah. It forces, like, it's a way of forcing the students to study. You have to make it cheat sheet.
Yeah. That's the thing, like,
Student for the average.
yeah, that's, I don't know, unless a professor somehow likes low averaging.
I really like solving podcasts. It's heavily.
Yeah, maybe that's it.
That could be a possibility. I had a problem like that, like having this curve, but physics 1B. No, it was his name was Fossey. It was like Russian guy. He like loved this curve. It hurt everyone down to the final.
One of my classes where like the average was huge, but yeah, I think the average was the same. But then he gave like sample that's nice. Yeah. So you really can get huge that like if you got like a literal it's not super great.
Well, yeah, we can't feel like that.
Yeah, it was really nice to see that though. It was really.
Oh, yeah. That cost can be tough. I mean, what we think of it. Yeah, pick 131. Yeah. I had it easier. So I honestly got really lucky. I got like a really nice prompt. It was like really lenient with exams, I think. Oh yeah, in my opinion, at least. Not everyone's opinion, but my opinion is. That made it a lot more than
Yeah, like you know, like there are many different possibilities. Like if you had a solution that they aren't good, you have a few flaws, but like
it gave a lot of credit for at least, or you can use it.
that's always nice. Like if it's clear, you get the basic idea of it. Yeah.
Oh yeah.
And it's like the one that we don't stress
I start up again. Oh,
yeah.
So, question?
Yeah.
Oh, cool.
Ask about the boundaries on.
Yeah.
Oh.
Yeah, I'll go through the slides again.
Yeah.
Yeah, I went through it a bit fast because it's not quite like, yeah, it's not the easiest thing to explain, but yeah, but yeah.
So like we're using that function to find the boundary.
So like you can imagine like the WTX plus B part is like in theory a line, right?
Oh, yes.
And so that line's not like actually the line we're using for the decision boundary, but like a transform version of that line is being used as a decision boundary where everything less than that is less than 0.5, everything other than 0.5. It's not exactly like it's a weirder line actual equation because like we apply sigmoid and e to the negative of it.
Yes.
So like the idea of having a line as a boundary is the key idea.
Okay.
Does that help? Like
And like where do we go back in boundary? What is back this boundary?
oh, I guess okay. This is more of like a conceptual idea right here. So like in your code or like maybe you're coding this, you're just gonna plug in like your x input into the function, multiply by WT plus b, sigmoid it, and then get your output and it's between 0 and 1, right? And if it's greater than 0.5, that's class 1, otherwise it's class 0. But like this is more like the idea behind behind logistic regression is that it's a probabilistic method.
Yeah.
And so the idea is that we're basically finding, where's that slide? We're finding P of y equals 1 given x, which is a conditional probability, which means that in a sense, it's making like a boundary system bound. It's like creating like it's creating like an optimal system boundary that like separates the classes. So it's like it's in a sense like maximum distance between the line. Like it's trying to maximize consistency basically. Like it's gonna be like a perfect middle between the two classes. So honestly, this line should be a bit more here. It should be like a perfect middle because of the nature of like predicting probabilistically in a sense.
And
Yeah.
there's all the some stuff.
Oh, this thing. Yeah. Or this equation
Oh,
is like
it's not part of sigmoid.
it's like what we're modeling with sigmoid in a sense.
Uh,
Like so like the goal of this whole model is to like create a function that does this, right? P of y equals 1 given x. That's our goal, right? We want to figure out, given the input, what's the chance of it being 1, right? And so this is our way of like creating a model that approximates that. Makes sense.
so we're using sigmoid to
Approximate
that
that kind of probably thing. And like it's a bit more in depth on like why that's happening. But I also probably don't know everything about why it's happening.
Yeah.
But that's the main idea, I would say. If that helps. Yeah.
Yeah.
Yeah. Good question about. All right. We can get started again. Oh yeah. Yeah, we are. Oh yeah, no worries. It'll be on the Linktree link at the beginning, this link. Oh, is it not? Okay, open it. So,
Never mind.
oh, okay, we're kind of slacking on this thing, but we will get them up there. Just if it's not up there by sometimes, like put a ping in. Like, are you in the Discord? Are you in Discord or yeah? Okay, it's like just like ping like people in Discord, but like I need the slides or whatever, or like being I don't know, yeah. But and then we'll get to it. It's just that yeah, we'll get the video up though. Yeah. All right. Go back. Spam. Okay. With the games in this one, right? Unpause the recording. All right, we're back. Oh, okay, so we didn't pause the recording. Oh well, we can edit that in post. Yeah, thanks. Cool. So, all right, we're gonna have a quick game to test your all understanding of this. I have to make it a count. You want to log in?
That's my
There you go. Right? You go.
yeah.
Yeah.
I guess so.
Yeah,
Yeah.
we're not weird. Yeah, in case they individually.
All right, let's just go with classic mode.
What's this thing on audio?
Wait, doesn't
Doesn't work. And then we're
thought we got it to work.
Oh well. All right, y'all can join up the link. Go to Kahoot. The individual.
Yeah, I'm just which I know this is full blast, but like
It's get better than nothing.
yeah,
The Kahoot, use it.
yeah, it's so like nostalgic. I swear. It's on max. Sorry, we wish that this thing had audio, but it doesn't. So, are you sure? It doesn't? Yeah, it's turned off. I would think. Yeah, just go ahead. All right, I think everyone's joined, so we're ready to.
Get started.
All right, let's get started.
First question, did Naman go to class today? What is it? Whoa, that's fast. Nice.
Nice.
Anyone want to explain why they said this for Candy? Yeah.
Pretty, yeah,
Alright,
that's like a, yeah, it's yes or no.
alright, so. Y'all come up at the end and we'll give you all Candy. Remember who you are. Alright,
All right,
nice. That was so fast.
yeah. Vish in the lead.
Alright, question 2. Similarly, who's the best CS pro? Alright.
Nice. Anyone want to explain for Candy? I know y'all want it.
Yeah, it's legit free candy.
All right, go ahead. Yeah.
Yeah.
Yeah, pretty much. Like there's Carrie, there's Professor Smallberg, there's Egger, like there's all these, yeah, multi-class. Okay. New leader.
Alright, what is the class in the first place?
Oh. Wait, the input's just the data, right?
Yeah, does
Okay.
someone want to explain why they picked red and also why they didn't pick green? Either or.
It's for Candy as well.
There's 4 of you who picked red.
Yeah.
So like kind of going back to the previous example, best professor,
Mhm.
you have like several kind of options to choose from. And
Yeah.
that's basically what the class is. It's like an output. So what are your options to choose from?
Yeah, I could ask why it's not green.
Yeah.
I guess another question is why is it not green? Like why is it not the inputs of an ML model? Yeah. Exactly. So like for example, like a professor's Bruin walk rating is not, it's not a class. It's not like you can't have a Bruin walk rating as a professor. Okay. New leader again.
What is outputted from logistic regression?
Be careful with this one.
Most of you got this right. Do people want to explain why it's not green? This is like a tricky question because it's like we are using sigmoid, but any thoughts? Why did you pick yellow or? Yeah, exactly.
Yeah.
Yeah. So like we're not outputting like a function, right? As you said, we're outputting like a value. And so we're not outputting the sigmoid function. We're outputting the output of the sigmoid function. We're applying the sigmoid function and then getting that and passing it out. Good job.
Yeah.
Alright.
Yeah. So, yeah. As we reviewed, logistic regression outputs a probability between 0 and 1. So, and a probability is always between 0 and 1. And
What function do we use to limit the output of logistic regression?
again, be careful here. With that, I'm actually curious, like who. That's it. They saw something. Anyway, okay, so it looks like most of you guys got that. Would anybody like to explain why it's not green? Yeah. Say, can you speak? Yeah, pretty much. So yeah, the sigmoid function is a function that for any x input, it returns a value between 0 and 1, which is exactly what we want to do. So we want to limit the output. So that's what we use it for. Oh,
Last one.
yeah. Now you get to answer.
You don't condone the blue one, actually. Other people like that.
Yeah.
You can say blue.
Say whatever you
Honestly,
want.
I agree with you all saying blue.
Damn, okay.
It's definitely the move. Definitely the move.
Yeah, I'm team green myself, but yeah.
Definitely the move.
Okay.
Game.
B plate. Yeah, I can vibe with it.
Alright.
All right, and number 3, Nathan. Number 2, Sean. And number 1, Messi, World Cup 2.0. All right.
Everyone who like answered questions or top 3, you're all can come and get Andrew and that one. I don't know who you are though. So. Just come down. Real quick. Top 3 or answer the question.
I'll leave these up for a few.
No candy. Okay.
Oh, that's a, wait, it's not all Starburst though.
Yeah, there's
There's
Kit Kats. There's Starburst and Kit Kat. I think that's the main thing.
Yeah.
They make everyone to come. Everyone hates Starburst. But then, really? How do you all hate Starburst? They're like, they're good.
yeah.
Yeah.
I love Starburst.
You.
Welcome. Okay. And now, right, nice. You want us to? Yeah. Once everyone's gone, then we'll do it. Okay.
Go back to slides.
Yep. Okay. All right. Okay.
Nice job, everyone. I think most you guys got that central idea to most of these questions, so I'm glad that you're all on the same page. For these small things. All right, so next thing we're going to move on to is actually like more model procedures, like dealing with actually how we're going to train our model. So the first part about that is a thing called labels, right? So we have our data set right here, these images, right? Cat, dog, chicken, cat again, chicken again, and fish. And so we're gonna feed these images into our model, right? We want to have a model that figure out, given the picture, what's actually in the picture, right? So what class it. And so what we're gonna do is that we're gonna assign classes to each of these like animal types, right? So we're gonna say a cat is 0, class 0, a dog is class 1, a fish is class 3, a chicken is class 2, right? And so for now, we're going to assign these numbers to classes. But there are some problems with this way. So what do you all think is a problem with labeling our images with the class number of the product? So like if you have like 100 classes, right? You have like a number for 100. What's the problem using the number itself of the class as label?
Yeah.
It's hard to tell, like, if there's so many numbers, it's hard to like remember which class.
That can be a problem with vectors and like the dictionary stuff that we can deal with that. That's a good point though.
Yeah.
Yeah. So this is a bigger problem, as well as the fact that sorry, you want to ask me for that? Okay. All right, so that along with the fact that like these outputs aren't like equally distant from each other, right? So if you predict like a 1 theory, let's say we didn't have signal, we can go any number, right? Like let's say we want to predict like a chicken, right? Is the chicken closer to the fish than the cat? Is that true? Not necessarily, right? And so we don't want to have these like distinctions for the data sets in this way, as well as I think all these when it's third one. And so we're not going to do this anymore. And so we're going to go on to the next slide. We're going to learn something called one-hot encoding. And so this is our new way of assigning labels or like what each image is to the images. So we're going to have things called one-hot vectors. Basically, it's going to be a vector of all zeros, but one of the indexes is going to be one. And that's it. That index is going to correspond to which class it is, right? And so class 0 is cat, class 1 is dog, chicken, fish. And so if it's a cat right here, the zero index is going to be a 1, everything else is going to be a 0. So this way, not only are we're getting by between 0 and 1, but we send only ones here, right? So it's between 0 and 1, 0 and 1, 0 and 1. So same way is good here, right? We're getting by between 0 and 1. And each of these data points are equally distant from each other. So like 1, 0, 0, 0, and 0, 1, 0, 0 onwards, they're all equally distant from each other, right? So we're not having any like weird connections between different numbers. And so these are the two benefits, or two of the benefits of one-hot encoding. Yeah. You mean for the label itself? Yeah, so for now, we're not going to do that, but we can do that in a sense if we're not sure about what the thing actually is. Or there's also this thing called like, there's like a way you can like have like more probabilistic labels in a sense. But this is like the standard way of living a data set. Like we know this is a cat, right? So it's 100% cat. Like we want our model to say that this is a cat, right? And so we're going to call it this. If we call it 0.2, 0.4, 0.6, 0.2, whatever you say, then it's not going to know what this is, right? It's going to think it's the dog or whatever, which is not. So usually for now, we're going to do it having like only a 1 in the top value, but there are like things that you can do. We can like have these not be 0, for example. Like we can have it at 0.9 with 0.7, different one. So like for now, I don't think it's like another way of doing this. Yeah, so we're going to do that for all of our data sets. So for each of these pictures, we're going to have a vector telling us which class it's in. And so depending on which class it is, we're going to set that index to 1. Is that clear to everyone? We're setting the index of the class to be 1, everything else is 0. That way we can figure out what the image is. Cool. And so now going back to our model, right? So we have our weights and our biases. And so our weights are a set of n features, or sorry, our inputs are a set of n features, right? And so we have x1, x2, xn. So for example, x1 could be like, how many eyes do you have? X2 could be like, do you like live underwater or on land, etc. These are features, right? And then we're gonna have a weight vector that we're gonna use this to figure out how important are these features, right? To figure out what the class is. So, for example, being underwater is really helpful to help your fish now, right? So that could be used in a way for our weights, for other things. And so we're gonna have our weight vector that matches the dimensionality of the input size. And then finally, when we do W transpose, so we're gonna transpose this to make it horizontal, multiply it by our input, we're gonna get a real value, right? Let me hit that one. We're gonna have a 1 by n vector times an n by 1 vector. We're gonna get 1 by 1 output. And so we can add our bias b to the actual scalar value. And so this is gonna be our binary model that we talked about last week. And so building on that, we have xy. A similar idea, multiclass. Now we're gonna have a bit more complications for like our output, right? So our output is no longer just scalar anymore, right? We're not taking through anymore. We're basically trying to pick classes, right? And so we had those vectors before, or one encoded vectors of like 1, 0, 0, 0, for example. And so we want to just figure out what's the probability of our class or of our image being one of the 4 classes, right? And so to do that, we're going to have to make our model a bit more complicated. And so our input is still the same n features, but now we have a bit more weights to basically figure out things per class, right? And so instead of our weight matrix being a 1 by n vector, instead, depending on how many classes we are going to have more weight. So like, you can think of like each, like column as being like, these are the weights for like class 1, class 2, class 3, class 4. So it's we're creating different weights for each class. So main idea here is that in order to encompass the fact that we're trying to figure out or distinguish between more classes, we're going to need more information on each class. And so we're going to have an n by c matrix, and it's the number of features and c number of classes. And so when we do an n by c or c by n, so we're going to transpose this. So c by n times n by 1, we're going to get a c by 1 vector, and we're going to add up our bias to get out. Does this make sense, everyone? The extension of our weights to a matrix. Yeah. All right. Move on then. So let's look at the actual example then. So we start with the image, right? So this is like a picture of a cat. You know, like a bunch of pixels in both ways, and we're gonna like flatten it into one long vector, right? But we're gonna like take all like the rows and like stack it together in one big vector. Those are the pixel values, right? And so now we have our input value x. These are our features, right? So like what each pixel value is, and then we're gonna move on to our weights. And so you see here that so that we have our weights here. We have 4 classes and pixel number of features, and so we have weight transpose is going to be a pixel coupled by pixel, right? We're going to multiply it by our input x in there, and we're going to add our bias. And so you see here, this turns into a 4x1 vector. So we can add this to another 4x1 vector and get this color. And so that gives us our scores, like our raw scores for the value. So like we have like these numbers for each class, but we don't know what they actually mean really because they're just numbers, right? So like what does 20 mean in context of 34? We don't really know what 24 means in context, but we're gonna apply a function to make this understandable. And so before that, we're gonna go into a quick question about what are the dimensions of the weights if we have f features, c classes, and yeah, basically, how you end up at GCP?
I first, so I training sample of the structure of the weight. So I noticed like Entropy, and then they use for the binary case, like for the softmax. So yeah, I'm doing the binary case. So that's kind of
Yeah, let's go through this fine. So yeah, as you said, number of samples, that just helps our weights get better. Doesn't determine how many weights we have. And so then we can possibly plot it out. And then the key distinction is that we don't want just one here because we're passing in. So remember the formula is W transpose x plus b. And we know that b should have a length of number of classes, right? And so we need WT times x. We need a vector of size classes by 1, right? 3 by 1. And so if we know that x is the size of size f, right? Then this is the only answer that makes sense, right? Because switching transpose makes a switch, so we got c by f times f by 1, we get c by 1. So that's also another way of thinking. Yeah. By the way, it is b in this case. Yeah. Cool. Any questions about the pipeline about going from the input to output? Right? Everyone go with the pipeline? Cool. In that case, we can move on to our next section, which is softmax, but comments can take that first.
We have a marker.
Clear?
I want to raise one of the.
Yeah, we can raise one of them. Yeah, go back to the green slide, and the up button, one of them.
Wait, actually, I turn on the also did the project. Okay. Just came down. Give us a sec. Wait, actually, it's just turned on. Hey, what's going on? We're trying to. Don't worry. Pull it back up. Let's not do anything.
Yeah, I saw that.
Okay, okay.
Try not to. I hope.
I can write on the white part at the bottom, it's fine. Yeah, but basically, so far Nikhil showed you all that if we have like an input, like image squished into like a vector, which is like pixels by one, right? Because each element is a pixel. And then we multiply it by this weights matrix in our multi-class model, then we'll end up with an output which is like this, right? And this is like the number of classes by one. So this is like, you can think of like each of these numbers referring to the model's prediction for each of these classes. So it thinks like, oh, it's like 23 worth a cat. It's like 9 worth a dog, for example, if the dog is the second class. Okay, but maybe in another case, the model outputs something like 1000 up here and like 2000 here. How would you like compare those relative values? Well, for that, to make it like more concrete than just like comparing these values, we use something called a softmax function. So what a softmax function does is it takes in a vector. So it's going to take in like maybe like your model's predictions, right? Like those Wx plus b's calculated by our models, and it's going to squish them into values between 0 and 1 in a special way so that all of the values add up to 1. Can anyone else think of another situation where like the values are all decimal and all the outcomes add up to 1? Where do you see that? Exactly, yeah. So in probability, you can have multiple outcomes, right? Like it's a like probability of it raining today or probability of it not raining today. But we know that if we add both those outcomes, the probability is still 1, right? So just like that, the softmax function ensures that once you apply the softmax function to like your model's output, and you get like your y hat, which is your prediction, the softmax function ensures that all the values are between 0 and 1, and they will all add up to 1. Just like probability outcomes would. And you can actually see that in mathematically because, okay, this is gonna be hard to, wait, can we remove this?
The what? The turn it off.
Yeah, the projector.
Like HDMI input. That's gonna lower it. Oh wait, I have an idea. Yeah. Now let me do this.
Okay, okay, unfortunately the projector is just refusing to switch off, but basically what happens is your numerator is going to be these values, so like either 3, 4, 1 or 2, e raised to 3 or e raised to 4, e raised to 1 or e raised to 2, and then in your denominator you're adding all of them up. So like you'll be adding e raised to 3 plus e raised to 4 plus e raised to 1 plus e raised to 2. Now there's a reason why we use e. And that is because E is always positive. So basically no matter what Z value like our model outputs, we want our probability to be between 0 and 1, right? So E is always a positive function. So just having like E raised to anything ensures that a probability is positive. So one of the reasons we take if the exponential function is because it's positive. Another reason is monotonically increasing. So the meaning behind monotonically increasing is that if you take any x on this graph, if you take any x, e to the x at that point will be lower than if you take like a higher x. So like it's an increasing function. So if you take like
x equals 2, the value of e to the x will be less than x at x equals 4, for example. That's the meaning of monotonically increasing. The reason we take like a monotonically increasing function intuitively is you can think of like the model is basically just trying to like optimize these numbers, okay? Like for example, if it spits out something like -1000, which is a really negative number, then e raised to -1000 is extremely close to 0. So essentially what the model is learning to do is if it thinks that the image that it's looking at, it doesn't belong to like a particular class. So for example, if it's looking at like the image of a dog and it thinks, oh, there's no way that's a cat, then it has every right to put like a really large negative number here. Because because the model thinks that the probability of it being is a cat is low anyway. So yeah, that's the intuition behind why we use like an increasing function, e exponent. Yeah, so basically, the key points here to remember are that all the probabilities add up to 1, just like in any probability situation, and these values are always between 0 and 1. So you could like take them as quite literally like a probability value. So this would be like, oh, there's a 24% chance this image is a cat, 64% chance it's a dog. So what most models do is they take like the most probable outcome. So this one would predict dog if like the second one is, if the second class is dog. If this was 0.64, then it would predict like chicken, for example, if that was chicken. But that's basically the intuition behind softmax. And basically what we have, we do wx plus b, and we get z1, z2, z3 to zc for our classes, the scores, to like kind of like do like shortcuts, to mathematical shortcuts to do softmax. What we do is what you'll learn in advanced track is a library called PyTorch. And in PyTorch, what you can do is you can apply the exponent function to, for example, each element of this vector. So we would use PyTorch to just apply the exponent, then we would divide by the numerator that we saw in the softmax function, and we would divide that by each of the elements. So then finally you would just get like some like a vector like this. These are basically just like vector operations to get the softmax values from the original values. Yeah, so this is not too important to know exactly how this works. But yeah, so that is softmax. Now I'm going to go into a cost function for multi-class classification. So in binary, like in logistic regression, when we had like two outcomes, like yes or no, or like dog or cat, we used the binary cross entropy loss. And so what you've introduced the binary cross entropy loss, right? Yeah. So basically what we do in multi-class classification is we use like a multi-class cross entropy loss. So the way the multi-class cross entropy loss works is through this formula right here. Basically this formula right here, it compares, it takes in your y hat right here. And this is your, so does everyone know what y and y hat are? Could someone tell me what y hat is? Yeah, the model's predictions, correct. And y is the actual label. So in our case, what you can think of like us applying our softmax and then finally getting this vector of probabilities. That is our y hat. That is like our model's ultimate output. So it's like this vector of probabilities, and our actual label looks something like this, right? It's one hot encoded. So it's not class 0, it's class 1, it's not class 2, it's not class 3. That's what this vector says. So we want some way of like looking at this prediction and saying, oh, how close is it to this vector right here? And this is like the multi-class cross entropy loss function. And what this does is it basically, you can kind of think of it as like, okay, so if you look at the first class is 0 up here. So y would be 0. So this entire thing becomes 0. And then let me actually see if I can get the board up, because it's hard to understand without. Oh, no. Jesus Christ. Okay. Wait, no. Let me see if I can type this out. Do we have like oh. Okay, no,
No, I want to. Sorry.
Okay, maybe I can present the intuition for this at the start of next class, but this cross entropy,
Sorry, give us.
it's okay. I don't think it's gonna work. But
Yeah.
I'll show you like the reasoning behind or like the intuition behind this loss function. Basically, it penalizes like in our case, if we are 1 and our model predicts close to like 0, then it would like heavily penalize that. But if we had something close to 0.8 here, which is relatively close to 1, predicting, oh, okay, is like predicting this class, then the loss is relatively low, as expected. And so the total loss across all training samples, you can kind of think of it as like just summing up the loss on each individual training sample. This is just like any loss function that we've done before. So basically, we're going to do the loss for the jth sample, but then we're going to do that for the first sample through the mth sample. So we're summing up all the losses and then we're dividing it by m. So that's just like summing up the losses and then taking like the mean. So this is like the mean loss right here. And this one right here is just like the expanded form. So if L is your multi-class cross entropy function, right? This is the one specified right here. Then if we plug in that formula for L here, this is our ultimate loss function. This is what it actually looks like. So from j equals 1 to m, we're summing over all our training samples, right? But I equals 1 to c it basically means that for each training sample, we are doing this cross entropy for each class. So for each class, we want to see how far it is from like its actual reality. So like if in this case, like the class 0 is 0, which means it's not a dog. So we want this to be close to 0. So this will like keep that into account. And then it will also keep the second one into account, the third one into account. So for all the classes, for each data point, it's going to evaluate like an entropy loss for each class. Like how far away are you from the truth of the class? So that's kind of like that's how cross entropy loss works in the multi-class case. And so if you look at gradient descent actually looks exactly like the binary version. So if you want to take the derivative of the loss with respect to our weights, it would end up looking like this again, because this is just like the multivariate logistic regression formula. Wait, Nikhil, that's right? Yeah. Yeah. And
Yeah, like the equations are the same because of the fact that like softmax is the generalization of sigmoid, and cross entropy loss is the same as binary cross entropy loss, but like generalized. And so we get the same losses no matter, or like basically the same losses, but in vector form or matrix form.
yeah, and as usual, like if you remember like a gradient, have you introduced gradient descent? Okay. So in gradient descent, we would simply like have our original weights. In our next iteration, what we'll do is we have our original weights, we have our loss, right? Then we compute like our DL by DW, which is like the gradient of the loss with respect to the weights, and then you just subtract that from the original weight. So this is like standard gradient descent, but the gradients the gradient of loss with respect to weights is given by this. And the gradient of loss with respect to the bias is given by this formula right here. And this is calculated using like multivariable differentiation. Well, yeah, which is slightly advanced for beginner track. In advanced track, you might look at some derivations of like just like the gradient. Cool, yeah. So putting it all together, since we are looking at logistic regression, if you recall, okay, yeah, is logistic regression supervised or unsupervised? Is it a type of supervised learning or unsupervised learning? Are you familiar with supervised versus unsupervised? Supervised learning is basically when your data has labels to attach, and unsupervised is when you don't have labels. So which one do you think we're doing right now? Right, this is supervised because each image has like the label of the image attached to it. An unsupervised problem is something where you have just like data points, you don't have a label, and you do some kind of like, you want to maybe like cluster similar points together. So for example, like if you have like Amazon's like user bases information, then then what you could do, for example, is look at each user's purchase history, run a clustering algorithm and try to group similar users together. In that case, so similar users would be like, oh, people who buy toys for their pets, or like people who buy textbooks for maths. They would be similar users because they buy similar products. In that case, we wouldn't have a label. So we would do something called unsupervised learning, where we just have we just have features essentially. And the model itself is supposed to find groups of data points which are close to each other. So it's so hard. Yeah, so just like you can kind of think of like plotting all the users of Amazon.com on like a 2D surface. You could have like pet owners in one corner because they're buying like all their food and toys for their pets. You could have like college students who are buying like stationery items or buying earphones and things like that. So that would be unsupervised. In this case though, since we are working with labels, since we know exactly what our each data point is, that's called supervised learning. In supervised learning, we have our we label in this case, we have one hot encoded the label because we are dealing with a multi-class problem. Could someone tell me the number of classes in our data set just by like this vector right here? 4, yeah, exactly. There are 4 vectors, which means there are 4 classes in my data set. But what I'm going to do is I'm going to take in this image right here. I'm going to squish it into a bunch of pixels. In advanced track, we will look at one algorithm called convolutional neural networks, which doesn't have to squish the pixels, which can actually just like look at different parts of the image. Stay tuned for that. But first, we squish the pixels. We apply the weights to the pixels, right? And we get some output like the Z, like the model, the one that model spits out. And then we use our softmax function, which kind of converts like the model's outputs into these probability outputs. And finally, we use like a cross entropy loss, like a multi-class cross entropy loss. We will compare this with, this is y hat, right? What will we compare this with when we want to compute our loss? With y. And what is y out here? This, yeah, so this is y. This is our ground truth. This is a model's prediction. In loss, we calculate the difference between a ground truth and a model's prediction. And so using cross entropy loss, we get some random value like this. And using like this gradient step, we will go back and update the weights, just so that the next time the model sees this image, it'll perform better than it did currently. Right now, it thinks it's a 24% chance of it a cat. Maybe like after seeing this loss, like which is maybe this is like a high loss for the model, it will go back, update its weights, and then maybe this probability will be higher. That's our hope. Cool. So, quick question. Your model outputs the following probabilities for multi-class classification. What is X? Not you, because you've been answering a lot of questions. What is your name, by the way? Nathan? 0.1? Yeah, that's right. Do you know, well, could you explain why? Exactly, yeah. So softmax again squishes all the values to add up to 1. So the answer for this one is 0.1. What was your name? Sean, thanks, Sean. Cool. That wraps up like all the content for this workshop. We have like an ethics part and then like a coding section that I'm going to quickly go through. So I think this is actually quite relevant to today. Like, how do we incorporate ethics into AI models right now? Because like, as you might have also read about ChatGPT, like ChatGPT has quite controversial things that like, even though like the developers of ChatGPT have blocked certain like pieces of information, certain keywords, like people have still found certain ways around to like very high security information, such as like how to make a bomb, or like even like racially insensitive information, things like that. So how would you design an AI system? Like ChatGPT was developed by like the best engineers, and they still couldn't develop something that was like robust and completely fair. So that just like raises the question. ChatGPT is basically just knows how to like create sentences from looking at like a bunch of text in the past. That's basically what ChatGPT is. It looked at a lot of text excerpts and like learned to like predict which sentence would follow, things like that. But AI can do a lot of things. Like you could like AI is also playing soccer these days. Like AI is being trained to play soccer. You could like that is also very like immediately transferable. Like if you can train a robot to play soccer, you could probably train a robot to like hit people or like do something physically. So like how do you like account for that when you're developing AI systems? So this is I think this is from like a book called the Asimov Foundations, if you read of that, if you heard of that. But basically these were like a set of rules that each robot must follow. It's just kind of interesting to think about. A robot cannot injure a human being. This must be like the first rule. A robot cannot injure a human being or through inaction allow a human to be harmed. You can kind of think of like counter examples here itself, like allow a human to be harmed is quite a gray area. Like how do you define that situation? Like is if a person is dropping a pencil on themselves and by deflecting the pencil, if you kill a cat, is that justified? Like so yeah, there's a lot of gray area here. And the biggest like issue is there's very little regulation regarding AI models. Like there is like a European organization which regulates the use of AI systems in Europe, but we don't have something of that sort in the United States yet. So there's a huge regulation issue with AI in general, because it's really hard to encode these kind of rules into any kind of AI model. Another cool experiment is a moral machine experiment. I'll actually just demonstrate just like one example of the moral machine experiment from MIT. Yeah, so basically, this was created as a result of like self-driving cars and like the growing like controversy surrounding self-driving cars is because self-driving cars, just like a normal driver, might have to face some situations where they have to make like one of two decisions. For example, in this moral machine exercise, they'll run you through like a bunch of examples where, oh, you either have to run over pedestrians who are like breaking the red light, or you run over like a kid and a dog who are like crossing the green light like at the correct time lawfully. So who would you run over in this case? Would you run over like someone older or someone younger? Would you run over someone healthier or someone non-healthier? Do you even get to decide like who you run over or who you harm? So yeah, the moral machine was a poll made based on that. And one of the most interesting aspects about this moral machine like exercise is that different cultures from different parts of the world, they have different like preferences or loyalty systems for people. So like some cultures value people of higher age more because they think they're people of higher status. So some cultures were like, oh, maybe we should protect like older people. Some cultures were like, we should always protect like the younger and healthier generations because the older have lived more. So it is actually not as simple as black and white. Oh, like this is the rule and everywhere in the world we have to follow it. There's actually a lot of like thinking that has to go behind this, behind any AI system that has any kind of impact on humans. Cool. Why don't we head into the coding part of today's workshop? Does anyone have any points or any like questions about what I just mentioned, about like developing fair AI systems? Okay, doesn't, oh yeah, sure. Oh, because, okay, that's a great question. The problem with moral systems is like, it's hard to like I mentioned here, like, for example, in these sets of rules, it seems like a robot would be like, a robot would be good if it followed these rules, you know, it's not harming humans. It must listen to humans unless it goes in conflict with this first law, like where it's harming humans. And then it can protect its existence as long as it doesn't conflict with the first two, which means as long as it's not harming humans and as long as it's not listening to humans. But then again, I also gave you one other example, like what if the robot is dealing with a situation where like the president is being shot or something, and it has to like divert the bullet and kill someone else instead. Like there are very, it's pretty yeah, there aren't any like moral systems in place at all. What people actually do, I took a class called CS 269 in UCLA. It's like a grad class on bias fairness in NLP. So a lot of deep learning, since it's reliant on your data sets, one of the things mentioned in that class was like having something called data statements, which elaborate exactly where your data set is flawed, like where, like which demographic groups is your data set not covering, which kind of niche like counterexamples does your data set not include, which your model might not learn? So like if you ensure that the data set you're training on is good, your model will generally be good. So that, yeah, so yeah, that's a great question. Also, like since you asked, like there was also like one risk assessment algorithm that was being used. It might still be being used in like some like courts across the states, but there was a risk assessment algorithm which was being used in some states across the United States in courts. And basically they used like a person's demographic information and their past crimes to predict to give them like a risk score, and it was extremely biased against Black people. So yeah, and they stopped using that because the data that was historically biased, which led to the algorithm being biased. So the algorithm itself wasn't really biased. So you can see how like AI can create multiple problems. Anyway, cool. So this is our multi-class classification notebook. Just like always, we'll be importing some important libraries. Let me know if you want me to explain any part of the code, or if you want me to explain, oh, what is this library for? I will gladly do so. In this first line right here, we're just importing our data set, which is the iris data set. Do we have internet here? Okay. Cool. Yeah. Does anyone want to tell me how many features our data has? Features? Okay. Do we usually use X or Y to talk about input? X. So what is our shape? What is the shape of X right now? What is our shape of X? It's 150,4. What that means is we have 150 data points in our data set, and each data point has 4 features. Yeah. So that's what it says. And Y has shape 150,0. What that means is Y has like a label, and the Y labels are either 0 or 1. And there are 150 of them because we have 150 data points. Wait, so do we know what is this an image data set?
This is like the iris data set. So this is like classifying like different flowers based on like different lengths that they're like sepal length, petal length, like that. So
yeah, so you can kind of think of, I'm guessing it has 2 classes.
I think it's 3 classes actually. So yeah.
Because Y has shape 150,
Maybe it is.
okay, so you can kind of think of this data set as like 2 classes of flowers, and one being 0 and one being 1.
Might turn into one part later.
Okay. And in right here, we're just dropping like 2 features. Basically, this data set has information like sepal length, petal length, like the petal length of the flower and things like that. And we're just dropping 2 of them. Let me show you which features we end up using. Cool. Let me plot this right now. So if I go and plot the data, this is what our data looks like. Again, we have 2 classes of flowers, and the features we're going to use are sepal length and sepal width. So if you don't know, wait, what is the sepal? Okay, the sepal is this part, like the leafy part is the sepal, and this part is the petal. Okay, so we'll be using the sepal length and the sepal width to predict which class of flowers the particular plant belongs to. So what we do here is we split our data set into some training data and some testing data. And then we have our logistic regression model, which we've already imported from sklearn right here. So we're gonna fit the model on our training data, and then we're gonna look at our training accuracy. Our testing accuracy. Our test accuracy looks like 1.0 right now, which is 100% accuracy. But does anyone want to tell me why that accuracy might be like misleading? This is 100% accuracy, but like why could this accuracy still be like misleading? So here is where I have where I split my data set into training and testing data. So I split my training data set into 80% training and 20% testing. So does anyone have any ideas why this test accuracy, which is maximum, by the way, could be misleading? Sorry? Close. So this test accuracy is only being done on 20% of the data set. So so this test accuracy is the accuracy of the model on just that small subset of the data set. So you can think of like, in our case, we actually have a very small data set, which is 150. So 20% of 150 is 30. So it's just looking at 30 images, and okay, maybe like by fluke, like some model could maybe like predict 100% accurately on 30 images, but it's really what's hard is to perform accurately on thousands or millions of images, and that's what ultimately we want a model to learn. And one way of doing that is by increasing the amount of data you have, just so the model looks at different types of images, for example, or different samples of data. So that's one way of like improving your model's accuracy. Anyway, why don't we look at our coefficients? So we have 4 coefficients, and I think so these coefficients correspond to X bin, Y bin. Bin, Y bin. Yeah, right here. Okay. So yeah, if you recall, our input data has shape 100,4. We have like 4 features, right? The 4 features we're looking at are petal length, petal width, and sepal length. Sepal width, we aren't plotting petal length and petal width, but this was just like an example I was showing you. So we have 4 features, so we have 4 coefficients, 1 coefficient corresponding to each one of those features. And then we also have the bias term, or the intercept, which our model has calculated. So you can like do binary model.coefficient to look at the coefficients, and .intercept to look at the intercept. But if we try to see what the model like visually did to our data, wait, what? Wait, why is the line back here? Okay, this line should actually be going through here. Let me see if there's an error in the code right now.
Slopes, right? What's the intercept? It's probably, wait, what's the intercept?
Intercept. Yeah, the intercept is probably wrong. Oh, slope. Zero.
That's right. What's the rest of it?
This one?
Where?
This one? Is that what you're saying?
I think it could be.
Intercept?
There's no, you can't index the intercept that much though.
Yeah. Okay. For now, we're gonna assume this line is going. Basically, what we did was we just used the coefficients right here. This is basically the slope of the line, and this is basically the intercept. For now, we're gonna assume that this line is going through right here. I think it probably got the sepal. I think it got like the sepal and the petal coefficients mixed up. So I think it might be using the petal one. Basically the line ends up going through here. And that is what we want a logistic regression model to learn. Like it needs to classify anything below this line right here. Below this line as class 1 and anything above as class 0. So the decision boundary is kind of like a visualization for what our logistic regression model is doing. And the decision boundary is actually passing right through the middle right here. I'm sorry that doesn't work correctly. Cool. But why don't we look at one multi-class classification example? So in the last example, we had 2 classes of flowers. In this example, we have 3 classes of flowers. And once again, we'll be splitting into training and testing. We have a multi-class model. So the logistic regression from scikit-learn, it lets you also work on multiple class data. So you can also use that the same model to fit on your multi-class training data. And then once we've trained on that data, we're gonna again look at our training test accuracy. Again, I'm very like explicitly mentioning this. We just have 150 data points in our data set. So like even the most basic of machine learning models can like get 100% accuracy on such small data sets. But to actually get like the best out of your models, you need larger data sets so that they can generalize well on new examples. Again, we'll be printing the coefficients. So does anyone want to tell me what the shape of this matrix is? The weights matrix? Does someone want to tell me? Someone except Sean? Oh, someone except Nathan, sorry. This is the weights matrix for multi-class classification. How many classes do we have right now? Like in our new example, how many classes do we have? 3. And how many features are we looking at for each data point? Exactly. So you can kind of think of each row. So each row is like the set of weights for one class. So this is the set of weights for class 0. The second one is a set of weights for class 1. The last one is set of weights for class 2. Each of them is going to do a WX plus B. This is going to be a WX plus B for the class 0, WX plus B for class 1, WX plus B for class 2. Does that make sense to everyone? Once it does that, it's gonna add in the bias term, of course. Do not forget the bias. Once it does that, it's gonna give you that thing that you put into the softmax function. So does anyone want to tell me, in our case, since we have 3 classes, what is our one hot vector gonna look like? Like what is the shape of our vector if we have 3 classes? What is the shape of Y if we have 3 classes? What is it? 3 by what? 1? Did you say 1? Okay, yeah, 3 by 1 is right. Yeah, so yeah, so they'll do WX plus B, right? We'll do that for each of the classes, and then we'll do the softmax. So that's what's happening basically internally. Cool. Why don't we look at this? What is the error here? X has 2 features. Let me see. XX. Did we not run this? Where do you mean?
Like when I was running it,
Uh-huh.
instead of being 104, it was 102.
Oh, like you dropped 2 features?
Yeah.
Is that what you're saying?
I think it's like
Oh, okay. Oh, wait, there we go. This is the line we wanted earlier. Thank you for that. This is the decision boundary when we have like 2 classes. So this is basically the boundary for the models. The decision boundary tells you, oh, below this, it's going to classify as 1 class. So even this data point would be a red data point in the eyes of the model. And above this is 1 class. This is just like a visualization for what the model is doing. So in our multi-class case, in our multi-class case, since we have 3 classes, we're kind of dividing like our entire like area containing all our points. We're dividing it into 3 clusters you can think of. So like this is the blue cluster, which is for one type of flowers. This is the yellow cluster for the one type of flowers, and the red cluster for one type of flowers. You might and I guess like the key thing to notice here, the key thing to note in general about logistic regression is that the green and the red points here, like even visually, they aren't like linearly separable. Like you can't draw a line and have them be like, oh, this side is 1 class and this side is 1 class. So that is one of the shortfalls of logistic regression. If your data like even visually, like you can run like some initial data analysis, right? When you're looking at your data set, if your data doesn't look like linearly separable, like if you can't draw a line separating the data, then logistic regression might not be like the best solution to your problem. And you might use something like a support vector machine with like, so and support vector machines basically come with like something called kernel transformations. They basically transform like, so basically if these are your points, support vector machines, what they do, like the kernel function, they can like arrange points radially. So like you can think of like a kernel function can maybe like convert like this like scattered thing. Actually, I don't know if you'll be able to see it. Let me actually show you an example of a kernel function online. Radial kernel function. Yeah, so you can kind of think of this example in this on this graph right here. If like a red and blue points were kind of overlapping, if they were not non-linearly separable, if you couldn't draw a line through them, then support vector machines, which are another type of algorithm, they come with like kernel functions. They can like transform your data into another shape. So like you could transform like lines into circles, and maybe in like this new circular space, like your data is separable by a line, because in this case you could draw a ring right here, right? So the SVM would do that. That's just like some intuition about the support vector machine. But what we learned about today was the logistic regression. What logistic regression serves to do is it serves to like draw lines between classes. That's what it does intuitively. But if you can't draw lines between classes, you might have like lower accuracy. For example, in this case, you might experience lower accuracy. Even though we have a test accuracy of, we do have a test accuracy of 93.3%, and that probably has to do with the fact that we can't separate linearly the green and red classes. If it did have 100%, that wouldn't be too like suspicious either, because we are working with a limited amount of data points again. So it's pretty easy for like any kind of a model to overfit on the small amount of data, but it's really hard for the model to overfit on a large amount of data. Cool. That does wrap up our coding portion. All of our links will be posted on our link tree. Our link tree contains like our beginner track resources and the recordings. Are there any questions about the coding section or like the support vector machine thing I said? Any kind of questions? Yeah.
I just had a quick question on about the color map.
Uh-huh.
So the green lines that are in between, like that are
Uh-huh.
the boundaries of each color.
Yeah.
Is that the logistic regression of like class 1 and class 2, class 0, class 1, class 0, class 2? Like is that like each?
So that is actually a great question. There are two types of logistic regression. It's one versus all and one versus one. I believe this one is one versus all. So in one versus all regression, basically what the model kind of intuitively does internally is it treats, so let's say you have cats, dogs, and lions, 3 classes. I'm just making it simple. Intuitively, what the model does is it looks at images of cats, and internally what it does is it learns how to classify an image as a cat or not a cat, but it doesn't learn about like cat, dog, or lion. And the second model would be, is it an image of a dog or not a dog? And the third model would be image of a lion or not a lion. So that is one versus all. And then 1 versus 1 is when you stack all of them up against each other. But basically what the decision boundary here is saying is I would have to like check up on this, like is scikit-learn Greg 1 versus all? It seems like scikit-learn uses the 1 versus all approach I just explained. And so you can, so I guess like intuitively what it would translate here would be like everything in here is the blue class, but everything outside is not the blue class. Everything in here is the red class, everything outside is not the red class. Everything in here is the green class, everything outside is not the green class. That's the intuition. Yeah. Do we have any other questions? About the theory or any of the code? Cool. I guess we'll wrap up here.
Thank you for coming.
Thank you for coming.
Thank you.
Stop recording.